Okay, good evening. This is the new topic. We still have three more topics in this subject. The last three topics, including this one, is road traffic noise control. Okay, and the major targets in this subject, I just want to share with you that how to do the assessments for road traffic noise. The documents for road traffic noise is similar to what we discussed before for railway traffic noise. Okay, because both documents they were issued from the Department of Transport in the UK, and this version is so simple. We just follows the guidelines. We are able to do the assessments. When we are talking about road traffic, okay, you may imagine that not only the noise pollution problem and also the air pollution problem. Okay, so in the past few years, our commercial brand proposed the use of this one. Okay, this one is a combination to reduce the air pollution problems and also the noise pollution problem. You can see that this headphone is to make use of active noise control. What does it mean? In the commercial markets, you can buy any different brands to have active noise control headphones. Active noise means that inside this one, not only it can generate and other sound effects, okay, to minimize the noise effects, external noise effects. Okay, this is what we call the destructive interference. And also, you can see that there is a filter here. It's similar to a mask. Okay, but actually, this product, I think that we do not need to use it. Okay. Okay, how to handle the road traffic noise problems and also the air pollution problem. Okay, let's take a look on this one. This is a kind of noise barrier, but this noise barrier, the surface area of this noise barrier, we use what we call a photocatalytic material. With the presence of this material, it can help to reduce the air pollution, certain air pollutants along traffic roads. Okay, this is to explain how it works. Actually, there are two layers. Okay. And the surface of each layer, we have some photocatalytic materials. With the presence of these materials under the sunlight effects, these coatings can change some pollutants into non-toxic materials. And also, it can perform as a sound barrier. Some countries already applied these technologies along the highways. In Hong Kong, we haven't applied this approach. Okay, now let's go back to this one. In the first half of this lecture, I want to share with you some general information about how to assess the road traffic noise effects and how about the current situations in Hong Kong. Okay, this is the data I extracted from the Department of Highway. You can find out the information here from this website. In Hong Kong, the total road length, the length is about 2,000 kilometer, compared with the railway level. In Hong Kong, the railway level is about 200 kilometer, maybe. So when you compare the road traffic levels and the railway traffic level, it is about 10 to 1. And this is the distributions because in Hong Kong, we mainly divided in three major parts. The first part is Hong Kong Islands in Kowloon and the New Territories. When you refer to this one, almost half of the kilometers in Hong Kong Islands and Kowloon, but you can see that the area distributions amongst three different areas, they are not equally distributed. So that's the major problems, especially the traffic congestion problems, mainly in the Hong Kong Islands and Kowloon. This is data. These are the data I extracted from the Department of the Environmental Protection Departments. Okay. Please bear in mind that when we assess the traffic noise, we use L10. Okay. As the indicator. L10. We don't want to have the road traffic noise level above 30 dBA. Okay. This is the recommended guidelines. But most of the areas in Hong Kong, even along the highways, okay, we are difficult to achieve this one. Okay. You can see that reference to this one, there are different districts here. The first one is Tsim Sha Tsui, Yau Ma Tei, and Wong Kok districts. You can see that more than 37.1%, more than 70 dB. Okay. We are suffering from the noise effects more than 70 dBA. Okay. According to L10. Please bear in mind that when we do the assessments for railway noise, we use the equivalence level, not L10. Okay, we use the equivalence level. But for road traffic noise, the common approach we use is L10 level. This is a three-dimensional noise map under the effect of road traffic in Hong Kong. There are different colors in this map. You can refer to this one. Okay, when you refer to the red color represents the L10 level is about 70 dB. Okay, so that according to the maps here, we can identify there are many areas. The level is about 30 dBA. Even for high-rise buildings, up to a certain level, the level is still is more than 70 dBA. Okay, so that's why it is a major problem in Hong Kong. Okay, this is Hong Kong Islands and this is the Kowloon Peninsula. Okay. Okay, when we follow the guidelines to do assessment, this is the we need to understand how to do this one, predictions of effects. Okay, we refer to the calculations of road traffic noise, and the short term is CRTN. Okay, and even when you refer to the EIA ordinance, okay, for example, chapter 499, you refer when we do the road traffic noise impact assessments, we still follow the approach presented in these documents. Okay, I will let you know why we use this one. There are different approaches around the world. This is the simple one and the common one we use it. Even now in Hong Kong, we still use this one because it is simple. And if we want to predict and approximate figures to for road traffic noise, it is a simple approach. And in Hong Kong, we still have another one, ordinary road traffic ordinance chapter 374. There are different terminologies defined in this chapter. We could not go through details about that. I just want to step on these documents because it is more useful for your study in the future. Okay, different from railway noise. There are three major parts. There are three major parts to generate road traffic noise, such as power unit noise, such as the heavy vehicles. I will let you know how to define what is heavy vehicle and what is light vehicle. And power unit noise can be generated from engines, brakes, gear, and the source. Noise emitted from the units of vehicles that take place in vehicles, including all mechanical noise effects. And the second one is what we call the rolling noise. Okay, is the interactions between the time and road noise. This is the rolling noise, similar to railways. Okay, the interactions between the wheels and the rail. And the third one is the wind noise, the noise emitted from air turbulence surrounding vehicles when traveling at a high speed. So, a question for you: which components can contribute higher traffic noise effects, A or B? Okay, you think that power units can contribute higher traffic noise effects or the rolling noise? Which one? It depends on the speed. Okay, take a look on this figure. The upper one is they are heavy vehicles, and the lower parts, this is a light vehicle. Okay, when you refer to this one, the y-axis is the noise level in terms of dBA. The black one is the rolling noise, and the gray one is the engine noise, and the blue one is the total one. Okay, when we increase the speed of vehicles, you can see that which one the rolling noise is more dominant than that of the engine noise. Okay, even for the heavy vehicles. Okay, you can see that the blue. But in the heavy vehicles, you can see that there is an intersection between these two noise effects. The engine noise is more dominant when we increase the speeds. Okay, the engine noise is still lower than that of the rolling noise. So at high speed, rolling noise is more dominant effects. Okay, in terms of the road traffic noise, when we compare with respect to the aircraft noise and the railway noise, some people did an analysis in terms of the annoyance. We used those response studies to see which one can contribute higher annoyance. When we increase, even we under the same level. Okay, the S-axis in this figure shows the level, but if you feel that three different types of vehicles, aircraft, road traffic, and trains, we found that aircraft can contribute higher annoyance than that when we compare with the road traffic noise and the railway noise. Okay, this is just this is based on the psychological effects. Okay, and effective overall plans for the reductions of road traffic noise. There are some general proposals or some general suggestions. The first one is that we may combine walking, cycling, and public transport. Especially in Hong Kong, this is a busy city. The government always encourage us to use the public transport instead of using private cars. And the major focus of this one is to promote the environmental-friendly transportation modes. The second one is to the speed reduction plans involving partial access zones, stabilize traffic flows, and reducing driving speed. Why we consider that this can reduce the noise effects. As I told you before, when we increase the speed, okay, rolling noise becomes more dominant. So that in some sensitivity zones, we need to limit the vehicular speeds. So that's why you can reduce the noise effects. Okay, another one is the traffic flow relocation plans. Bypass roads. What is bypass roads? Bypass road is that we may make use of tunnels. Okay, this is a bypass road. For example, in Hong Kong, we have a famous bypass road in the Hong Kong Islands. Okay, this is the Central Wan Chai bypass. Okay, this one, the major targets for this one is to reduce the traffic flow, to reduce the traffic congestions between Central Wan Chai and other areas in the Hong Kong Islands. The total length is about 4.5 kilometers long. Okay, and this is a dual free link track road. And you can see that this is the map to show the whole sections of this central link. One of the major issues inside this one is that this is a tunnel. With the presence of these tunnels, we can reduce the traffic noise effects. But another one is that when we design a tunnel, we need to make sure that there are two major issues. The first one is the fire safety issue, okay? Because you know that every car is fire low. In case of fire accidents, how to make sure that we can maintain a clear aspiration towards this is a problem. The second one is that even under the normal situations, we need to maintain good air quality inside this tunnel, okay? So that's why you can see that in reference to this map, we have the ventilation building here. In the west and in the east. Okay, these two ventilation buildings, they are used to make sure that the air quality inside these tunnels are under a normal level. Okay, so that's when we design a tunnel refers to the environmental effects. We may consider two aspects. The first one is the fire safety issue. We have a very large smoke extraction system. Okay, in case of fires, we need to maintain a good visions for our explorations. And the second one, even under normal situations, we have to make sure that the tunnel in every point we can maintain a good air quality. Okay, this is the third point, and the next one is plans to relocate noise black spots, such as to optimize traffic signals. Why we can optimize traffic signals can reduce noise level, because you know that one of the major source from vehicles is from the engines. Okay, so that if we cannot optimize the traffic signals, there are many traffic lights. Let's say, okay, the decelerations and accelerations of vehicles. This is the major noise effects. Okay. So that we can make sure that we can smooth the traffic flows along the roads. You can help to reduce the noise effects. And the traffic volume optimization plans is we need to provide sufficient parking spaces. This is a major issue from Hong Kong, because you know that we are shortage on areas, and even during the weekends when you go outside, such as shopping malls, we don't have sufficient parking areas. And the third one, and the last one is that to improve road services and maintenance, such as we may propose the use of the no-noise road services. What is that? No-noise road services is that there are some porous materials along the pavements, because these porous materials can help to absorb the noise effects, so that this can reduce about 3 to 4 dB. 3 to 4 dB. Okay, in terms of the vehicle noise control, we may consider that the import of the no-noise vehicles. We have more stringent requirements. When you refer to this figure, you can see that the red one it refers to the current standard, and the blue one it refers to the old standards. When we import motor vehicles, we can make use of, we need to follow the current situations. We always encourage the use of the electric cars, because you know that for the electric cars, we don't have many engines, so that you can reduce the engine's noise effects. But we cannot reduce the rolling noise effects, because the rolling noise is mainly from the interactions between the types and road services. And we want to adjust the existing traffic noise problem through abatement programs and get the public and other stakeholders involved through education, engagement, and partnership program. All of them, they are some general guidelines. Okay, road noise impacts, it depends on road alignments. We want to provide sufficient distance separations between the noise receiver and vehicles. Noise receiver here, it refers to any buildings or any sensitive receivers. The second one is the traffic compositions of volume. It can provide the traffic planners and management to control vehicles, movements, and vehicle types. The third one is that we want to provide some noise tolerance buildings, such as multiple story car park. Please bear in mind that the provisions of multi-story car park building, this is not the major issue to reduce the noise effects. We just want to make use, we can use this one as one of the mitigation measures to reduce noise effects. And because you know what is shallow zone? Shallow zone is that I explained before to you. If we have a receiver here, okay, if we have a sound source and this is the receiver, if we install a barrier in between the source and the receiver, how to define the shallow zone? The shallow zone is that we draw a straight line here. Below this line, this is shallow zone. Okay, above this line, this is what we call the illuminated zone. Okay, the concept here is similar to the barrier. Okay, we use the multiple car park building. The residential building sitting on this multiple car park buildings. This is similar to a barrier. And we have to provide the screening structures such as some barriers, road enclosures, and road deckings to reduce noise effects. Okay, this table I extracted from chapter number 9 from the Hong Kong Planning Standards and Guidelines. I discussed this one before to you in aircraft noise and also the railway noise. Please pay attention now. In terms of the road traffic noise, we use L10 for 1 hour as an indicator, and the maximum level we suggested is 70 dB. It means that it is better to maintain the level under 70 dB. For example, for domestic premises, the acceptable L10 level is under 70 dB. For educational institutions such as our campus, it should be lower than 65 dB. And for hospitals, it is recommended to lower than 55 dBA. Okay, so that's the maximum one is 70. This is the acceptable level. More than that, how to consider this one? We may use another mitigation measures such as the provisions of noise barriers, the use of the window glasses, or something like that. Okay, reference to this document, there are some tables relevant to the road designs. This is general design information. For example, if the peak traffic flow, this is in terms of this table, the y-axis here, the vertical column here, this is the peak hour traffic flow in terms of vehicles per hour. If the vehicles per hour is 1,000 and the vehicular speed, let's say, is 70, the values here is 78. Okay, 78. Please pay attention. This is the facade noise level L10 in 1 hour. And what is the facade noise level? It means that's the assessment points, which is 1 meter away from the building facade. Okay, we could not do the assessments inside buildings. Okay, because inside buildings there are many reflective surfaces or absorptive surfaces. So let's say if the peak hour traffic flow is 1,000 vehicles per hour and the vehicular speed is 70, the level we estimate is 78. But the guidelines told us that the recommended level, the maximum level is 70. How we can solve these problems? We may propose the use of noise barriers or other mitigation measures in such a way that it can be reduced to within 70 dBA. Okay, in terms of road noise designs, I just want to introduce some of the terminologies to you. The first one is the trunk roads. This is similar to an expressway, the highway. The second one is the primary distributed roads. This is a carriageway roads similar to the trunk roads. And the third one is the district distributed road. This is to connect in between the primary road networks and district within the urban area. And the final one is the local distributed roads. The meaning of that is given direct access from the district distributed. That means this one and to your home. Okay, why we need to consider these 4 terminologies? Because there is another table here. Okay, this is the road type. Let's say if the primary distributed, the traffic flow is 3,000 vehicles per hour and the vehicular speed is 50 km per hour. The distance separations to fulfill L10 in 1 hour for 70 dBA. Without any screening structure, we need to have 180 meters separation. If we have a screening structure, it can be reduced to 40 meters. Okay, but both of the conditions we are difficult to achieve it because the separations, because the space in Hong Kong is limited. So this is just for your reference, and they are based on some standard acoustic knowledge to do calculations here. Okay, how to do the road traffic monitoring methods? There are 2 approaches. The first one is the vehicle pass-by methods, and the second one is the close proximity method. What is the difference between them? Let's take a look on the first one. Vehicle pass-by methods, it means that the schematic diagram shows that the testing methods here. We put 2 microphones along the roads here, and when this car passes by this zone, okay, we can measure the noise effects. And there are some general guidelines here. The microphone should have 7.5 meters away from the center of this testing track, and the microphone should be at 1.2 meters height above ground, and around 15 meters open area. We should not have any other obstacles. Okay, let's take a look in reality how to do this vehicle pass-by methods. Okay, this is. Okay, here is the standard test. Okay, we put 2 microphones along the track, the test track. Okay, and then when this driver almost arrives this test track, okay, he could turn off the engine. He could turn off the engine because one of the sources is due to the engines. Okay, we just want to check the volume noise effects. And you can see that around the this test track, this is an open area, and according to some general guidelines, they propose that 50 meters open area should be provided. This is the first one. And the second one is what we call the CPS, close proximities method. What is that? Because when we want to test the road surface, the road pavement along the real situations, we cannot make use of the we call pass-by methods. For example, if we want to test the highway along PolyU campus, we cannot make use of this one. We may make use of the CPS approach. What's that? There is a trailer here. This trailer, inside the trailers, we can install different types of times inside this trailer. And along the trailers, we install microphones along this one to check the variations between the rolling noise. And this is a method based on the test time, rollings on the road surface, and the test track surface. We can measure here. CPS is taken on a trailer. This is what we call the trailer. And inside this one, we install some absorptive materials, not reflective materials. This is similar to our semi-electronic chambers. Okay, when you install absorptive materials here, the noise effects generated from the time and the road surface, it can be absorbed. And it could not affect the measurement results. And the trailers includes a hood over the microphone such that wind noise can be reduced and noise from other traffic can be reflected. We have guidelines and standards to show how we can do the standard measurements. We could not follow the details about that. We just need to understand the working principles for this CPS approach. The major advantage of using this one is that the effect of the noise source, such as engine and exhaust sound, can be minimized. But the limitation is that because in every time we can only install one type of time inside this trailer. Okay, so that if we want to test another one, we need to replace another one. Okay, so that this method is made with a limited set of times at one weight. Therefore, it does not account for the vehicle's variations typical of traffic streams. Okay, this is a CPS testing approach under our department. Okay, Doppler effects. In the past, we just consider all the sound sources, they are stationary. They are stationary. It means that they cannot move. Okay. For example, if we have a loudspeaker, and even now I'm talking with you, this is a stationary noise source or sound source. Okay. But why we need to study the Doppler effects? Doppler effects is to use to assess the moving source, because you know that no matter this is a railway or a vehicle car, this when it generates sound effects, this is a moving source. Okay. What is the difference between a stationary source or moving source? We need to consider this effects. This is what we call the Doppler effects. It refers to the change in frequency of the wave. Why, if we consider there is a change in frequency, why we need to consider this one? Because you can. Okay, let's take a look on this one, this figure. If this is a stationary source, okay, it generates sound fields in all directions. The wavelength here, they are in equal distance, correct? But if you can consider that this is a moving source to the right-hand side, it generates the sound wave patterns like this one. You can compare the wavelength here with respect to this one. This portion is longer than this one, correct? If there is change in terms of the wavelength, what happens? There is a change in frequency. In the first lecture, I told you that C is equal to F lambda, correct? If we change this parameter, these parameters could also be changed because this is a constant value. So that in this case, here, when our moving source is in this direction, okay, the wavelength is reduced. That means the frequency is increased in this case. But on the other hand, at the end of this moving source, because the wavelength is longer, so the frequency could be decreased. Okay, the similar situation is like this. There is a train from this station to another station. When this train almost approaches these new stations and it generates the sound effects, with respect to the shorter wavelength, what could happen? The frequency is higher. Okay, when we stand here, okay, to listen to the sound effects. But on the other hand, if we stand here, okay, because the train is moving away from these stations with longer wavelength, the frequency we can hear the sound effects is lower. Okay, so that if we consider there is a moving source, the frequency could be changed. But if this is a stationary source, there is no change. There is no change in terms of frequency. Okay. Okay, this is a similar situations I wanted to share with you. There is a car moving towards us. This is the sound effects. Okay, when we have a car moving to us, okay, the frequency could be changed. Okay, because the wavelength from this sound effects is also changed. Okay, how to do the calculation for this one? We may skip all of them. We can go to this figure. Okay, how to read these situations? There are 4 figures here. We just need to consider one of them so that you can identify other of them. Okay, let me show you what are the definitions for this one. We here, let's take a look. We represent the speed of sound. What is the critical values for the speed of sound? 344. Okay, this is the critical value. How about U naught? What does it mean? U naught, it means that the observer speed. And how about US? US is the source speed. Okay, the moving speed. Okay, so let's take a look on the first one. Okay, the left-hand side, the upper one. We need to consider this equation. In this equation, what is the F here? F is the frequency generated from the source. And F pi, it means that the detected frequency. Let's say a student is coming here, okay, and his mobile phone is ringing. Okay, I can hear the sound effects. If here is the sound source, correct? And here is the moving source. Okay, so that's the smartphone is ringing. The sound effect is F, the frequency generated from this mobile phone, and F pi is the frequency I can detect. Okay, when you compare this one and this one, what is the difference? What is the difference between the first 2 figures here? Okay, you can see that the only difference is that US, the source, this one is moving up. Please do not consider that this is moving to the right or to the left. You may consider that in this situation, the source is moving to the observer, and the observer is moving away from the source. Okay, we do not consider going to the right-hand side or left-hand side. We just consider that the source is moving to you, to approach you, or moving away from you. Okay. So when you consider the first 2 figures here, the only difference is the source. Okay, this one is moving to the observer, and this one is moving away from the observer, correct? So when you compare these 2 equations, the only difference is that the minus side, it becomes to the positive side. Okay. Okay, this one. if you just memorize the first situation like this, if you consider the second one, the only difference between the first one and the second one is this one, US. So if this is negative, we change it to positive. Only the negative side to positive side. Okay, when you compare the first one and the third one, what is the difference? The difference is that the source is moving to the observer, and also the observer is moving to the source. So the change is this one. Okay, from negative side to positive side. Okay, when you consider the last one, the green one, okay, when you compare the first one and the last one, the only difference between them is that this one is moving to the observer, but this one is moving away from the observer. So that we change the lower part from negative to positive. And how about the observer? This one is moving away from the source, and this one is moving to the source. So that we change the negative side to the positive side. Okay, you just need to identify one of the scenarios here. You can identify other scenarios. Okay, any problem? Okay, let me show you an example. Okay, like this one. Example number one. We have a car, it's moving towards a man, and the sun is on. Okay, the car, this is the sound source. This is the sound source because the car generates the sound effect. Okay, not this guy. Okay, so we define this is US. And this one, this is the observer. We can hear the sound effects, so we consider that this man is this man is an observer. So the situation is like this one. The source is moving to this observer, like this one, and this one, this guy, this observer is moving away from this observer. Okay, so when we encounter this situation, we need to use this equation. Remember, the arrow here, they are not used to represent to the left-hand side or right-hand side. We just consider that to follow the observer to away from the observer. Okay. Okay. For the second one, there is a train is moving away from a stationary beamforming system. Okay, like this. This is the beamforming system, and this train is moving away from this one. The beamforming system is the observer, and the source is this train. So that we make use of this one. Okay. In this one, in this case, because the detection system is fixed and stationary, so that the speed of this observer is equal to zero. Equal to zero. Okay. No any speed. When you consider this equation, we can directly set u naught is equal to zero. Okay, can you consider this one? Can you understand how to convert these descriptions to the equations here? Okay, let me show you an example. We have a concrete car traveling at 60 km/h, and its is on at 670 Hz as it approaches to a worker in a construction site. What will the frequency be received by the worker walking towards the car with 1 meter per second? Okay, when you do the analysis for this one, first of all, you have to change the speed of the observer and the speed of the source in terms of meter per second. Okay. So the first one is to change the units in terms of meter per second. The sound speed here is 340 meter per second. And where is the observer speed? The observer speed is 1 meter per second, correct? Okay, this is the worker. The worker is an observer. Okay, we have 4 scenarios, correct? Okay, let's take a look which one we should consider. The source effect is moving to the worker, to the observer, okay? And the worker is also moving to the car. When you consider these 4 cases, which one is correct? This one, okay? Because the car is moving to the worker, and the worker is also moving to the car. So you have to use this one. Please bear in mind that you cannot set the positive side or negative side by yourself, okay? If you pick this one, if you consider this one, okay, you can derive in other cases. If you consider this one, you can derive all other 3 cases, okay? So in our example here, we consider this equation. The speed of sound is 340 meter per second square. The source speed is 16.7 meter per second, and the observer speed is 1 meter per second. Okay, and then we call this equation. We call this equation, and then you can substitute all the data, all the values given here to these equations. You can find out that the detected frequency received by the worker, it becomes 706.7 hertz. 706.7 hertz. Okay, when you consider these situations, the generated frequency from the car is 670, but the detected frequency received by the worker, it becomes higher, correct? What's the reason? You can consider this figure. Let's say this is a car, okay? This is a moving car, and we stand here. This is the worker. Because when a car is moving to this worker and generating a sound effect, the wavelength here is shorter. The wavelength here is shorter, so that the worker can hear higher sound effects, high frequency sound effects. Okay, if a car generates the frequency is this one, 670 hertz, this guy can hear the sound effects is 706.7 hertz, okay, with higher sound effects, high frequency effects. Any problem? So that's when you refer to similar types of equations or questions, you need to identify and you need to analyze what types of situations we have. We have 4 cases. If you can identify one of them, you can derive another type. Okay, any problem about this one? Okay, let's take a break first. If you have any problems about this part, you may ask me. Okay, let's come back. Although we have 4 cases here, if both of them, both the source and the observer, they are stationary. What does it mean? Let's say we take the first equations here. If u0, this one is equals to 0, and this one, the source, is also a stationary. Okay, it means that the detected frequency is exactly equals to the generated frequency. Okay, so that if you consider that there is a stationary source, there is no change in terms of frequency and wavelength. Only the situations we consider that if we have a moving source or moving observer, there is a change in terms of the frequency. But when we consider the building acoustics, we seldom consider the moving source. Okay, normally when we consider road traffic noise or railway traffic noise, we consider the moving source. Any problem about this one? Okay, let's go to the second part. Our target is on this one. The calculations of road traffic noise. This document can help us to do analysis for the effects of road traffic noise from existing road on future sensitivity developments, or we can make use of this one to assess the effects of traffic noise from future roads on existing sensitive developments. Similar to the calculations of road traffic noise, we still consider numbers of factors, including traffic volume and speed, mode surface corrections, distance, ground effects, whether this is a soft type or hard type, soft type such as grassland, and hard type such as concrete pavement, and there are any barriers or reflection effects. Okay, you may ask, is it reliable or accurate for using this document? Some scholars, they did an analysis for using CSE and compare with the real assessments. They find that the coefficients can be up to 0.7. The maximum is 1. Okay, so that even we apply this simple predictions approach, we can evaluate an accurate result. Okay, if you are interested in this one, you can find out this paper for your study. Okay, let's go to the basic indicator for this one. What is L10? L10, it means that at least 10% of the total time durations, the level existed a certain level. For example, 70 dBA, what does it mean? It means that at least 10% of the total durations here, the level is above 70 dBA. This is what we call the L10. And normally we consider that this is the peak level. Okay. And how about L90? What's the meaning of L90? L90, we generally consider that this is the background noise level. Okay, because 90% of the time durations, the level is about certain value. Remember, when we do any analysis for this environmental assessment, the unit is in terms of dBA, and the assessment point is taken to be 1 meter away from building facade. And the traffic noise, the standard is 70 dBA. When what does it mean? It means that when the limit is just met, traffic noise will exceed 70 dBA for 10% on an hour. Okay, if you consider 1 hour, it means that at least 6 minutes, the level is about 70 dBA. Okay, for the remaining time, that means the rest of them, the traffic noise will be less than 70 dBA. This is the definition for L10. Okay, there are 2 parts when we do the analysis for road traffic noise. Compared to the railway traffic noise, we just have 5 stages. In railway noise assessment, we have a total number of 6 stages. So if you classify into 2 types, we can consider that the overall calculated noise level is equals to the emissions model and the propagations model. Okay, what is the emissions model? It depends on the reference value, and the propagations model, it refers to the corrections for distance barriers or others, such as angle view. When you take a look on this flow chart, the first one is to divide road scheme into segments. It depends on real situations. I explained to you before, if there is a noise barrier in between the roads, okay, we need to divide into 2 parts. The second one is the basic noise level. When you reverse this skyline, there are 2 indicators. The first one, both of them, they are in terms of L10, but this one, the first one is for 1 hour only, and the other one is for 18 hours. Okay, we seldom use the second one. Okay, we normally use the first one. And the corrections factors we could consider include flow, the vehicular traffic flow, speed, percentage of heavy vehicles. This one is the heavy vehicles, percentage of heavy vehicles. You may ask the questions how to define what is heavy vehicles. We need to have a standard approach to define it. I will explain to you later. And gradient and mode surface. After that, we can go to stage number 3. Is about the propagations effects. And stage number 4 is site layout. There are 2 corrections factors. The first one, corrections for reflections. Still remember that because the assessment points is 1 meter away from the building facade, because the surface or this facade or this building facade is a reflective surface, so that we need to take reflections corrections into this effect. Okay, normally we take 2.5 dBA for our analysis. And finally, you have to combine all contributions from each segment. Okay, if you just have one single segment, you do not need to consider stage number 5. If there are 2 or more segments, you need to combine all of them together. Okay, this is the whole procedure. In the tutorial tonight, I will share with you how to apply this one to do the analysis. Okay, in terms of the predicted noise level, we could consider all of them. But when you do similar problems in your tutorial and even in your final exam, you need to pay attention to the information presented in the questions. Okay, sometimes not all corrections factors we need to cater for it. Okay, the scenario is like this one. We have a road, and this road is in parallel with this receiver. Okay, and the assessment point is 1 meter away from the building facade. Okay, let's take a look one by one. The first one is to find out the basic noise level. It depends on, this is a function of 3 parameters. The first one is traffic flow. The units Q, the bit letter Q here is in terms of vehicles, how many vehicles per each hour. The second one is percentage of heavy vehicles. How to define heavy vehicles? If our vehicle, the unladen weight is more than 1,525 kilograms, we consider this as a heavy vehicle. What's unladen weight? It means that no any passengers. The empty weight on a vehicle. If the empty weight on a vehicle is more than that, we can classify this as a heavy vehicle. Okay. And the traffic speed is kilometer per hour. Okay, so that's the basic noise level is 42.2 times 10 times not Q. Q is the traffic flow. And the corrections for heavy vehicles and speed, we may make use of these equations. Please bear in mind, all the equations presented here could be given if we have similar problems. Okay, you do not need to memorize all these equations, but you need to know how to make use of it. Okay, and the first one is to find out the basic noise level, and the second equation here is to do corrections for heavy vehicles and speed. When you refer to the second equations here, there are two parameters. The first one is p, and the second one is v. V is the traffic speed in terms of kilometer per hour. I just want to remind you p here. If I tell you the percentage is 20%, do not change it into 0.2 and substitute into this equation. You just substitute 20 into this equation. Okay, because in these equations the units p is percentage. Okay, I repeat again. If I tell you the percentage of heavy vehicles is 20%, you just directly substitute 20 into these equations. Do not change it into 0.2. This is not correct. Okay, because p, the units in this equation is in terms of percentage. Any problem? Okay, now we go to this one. Chart number 2, this is for hourly rates. This is L10 for 1 hour. And chart number 3, this is L10 for 18 hours. Okay, they are different. We seldom use chart number 3 because normally, even for in Hong Kong, we could use L10 for 1 hour for our assessments. Okay, so from time to time, we could take chart number 2 as a reference. Chart number 2, you can make use of these charts or these equations to find out the basic level. 42.2 times 10 power not Q. Q here, this one is the total flow. This is the same as the big letter Q here. Okay, they're the same. Any problem about this one? This is a linear relationship between the basic noise level and the total flow, okay, in terms of how many vehicles per each hour. Okay, now for chart number 4, how to read this one? For chart number 4, you can either use this equation or this chart to find out the corrections factor. Reference to how to read this one, how to read this chart. This is the corrections factor, okay? The x-axis is the traffic speed, correct? In terms of how many kilometer per hour. And how about this one? This is the percentage of heavy vehicles. Okay, now, if the situation is like that, the percentage of heavy vehicles is 20%, and the vehicular flow is 50 km per hour, and there is no gradient. When you read the data from this chart, okay, this is 50, correct? And the percentage of heavy vehicle, this is 0, 5, 10, and 20. So this is the intersection points. This one. When you got the intersection points here, you can draw horizontal lines to locate the corrections factor. The corrections factor here is about 1.9 dBA, correct? You can try it by yourself by substitute p is equal to 20 into this equation, and okay, p is equal to 20%. And v, what is v? V is equal to 50 km per hour. Okay, you can get similar results here, around 1.9 dBA. Okay, any problem? Okay, any problem? How to read this one? We just have considered two parameters, the percentage of heavy vehicle and the traffic speed. Okay, this is for chart number 4 without any gradient. How about if we have a gradient? Okay, the road has a gradient moving upward or moving downward. How we can cater for this one? Let's say for another case, if the percentage of heavy vehicles is still the same 20% and the vehicular flow is 50 km per hour, but now the gradient, the upward flow, this is upward flow, not downward flow. Okay, let us consider the first scenario, upward flow, 5%. You need to consider chart number 5 first. How to consider this one? Now, the gradient percentage given here, the upward flow is 5%. This is 5%, correct? And how about the percentage of heavy vehicles? 20. Okay, this is the intersection points here between the road gradients and also the percentage of heavy vehicles. So that's the change in mean speed. When you read the data along this vertical axis, what is the value here? About 5.7, correct? Okay, this is 5, this is 6, and this is 7. Okay, so that's the change. What is the meaning of delta V? This is the change in mean traffic speed. The value is about 5.7. So the original speed is 50 km per hour. You should use the original minus the change in the mean speed is equal to the real situation, 44.3. Why? If we have an upward flow, okay, if you drive a car in upward flow, the speed could be reduced, correct? If you drive a car along the upward gradient, the speed could be reduced. So this one is to make corrections for that reason. There is a remark here. This table is not applicable to downward flow because for downward flow, you need to use the brake to control the speed. Otherwise, it could be increased. Okay, this is just for upward flow. Okay, now you got the data 44.3 km per hour in this case under the upward gradient 5%, and then you go back to this chart. Now you have to choose the values mean traffic speed 44.3 and 20% and locate the corrections factor again. Okay, if we just have a road gradient, if we have a road gradient 0%, we can go to use chart number 4 directly. If there is a road gradient for upward flow, you have to consider the use of chart number 5 first to make an adjustment for the vehicular flow, and then go back to use the chart number 4 to find out the corresponding corrections factor. Okay, any problem? Any problem about this one? Now in this case, this is 5%, and the adjusted vehicular flow is 44.3. So the value V here in this equation, it becomes 44.3 km per hour instead of 50. But for downward flow, you do not need to consider this one. Okay, you do not need to consider chart number 5. You can go to chart number 4 directly, because when we go downward, we need to make use of the brake to control the speed. Any problem about this one? Okay, now the other corrections is the row gradient corrections. The row gradient corrections, this is a linear relationship, and you can make use of this chart or this equation. Please pay attention. This is 0.3 times g. G is in terms of percentage. In terms of percentage, let's say if this is 5%, okay, when you use this equations, this it becomes 0.3 times 5. Okay, it becomes 1.5 dBA. 1.5 dBA. You can check this one. If the percentage gradient is here, the correction factor is 1.5 dBA. But this one is g is the gradient in percentage. We just consider the upward traffic flow only. Okay, when we move upward, if the gradient is moving downward, we do not need to consider this one. That's the same reason. Okay, we need to use the brake to control the car speed when you go downward. Okay, but for going upward, if we want to maintain the same speed, let's say now the vehicular speed is 50 kilometer per hour. If we want to keep this one when we go upward, we need to add more power to the car. If we increase the power, what happens? You can enhance the power noise effects, because power units is one of the major sources to create noise effects. Okay, so the design intent for this one is to handle the cases for power engine noise effects. Okay, but for when you go downward, okay, we do not need to increase the power. We need to control the brake. Okay, in this case, we do not need to consider the corrections for this one. And there is a last statement here. G can be up to 15% only. Okay, 15%, more than 15%. We need to do real measurements. Okay, we cannot make use of this simple extrapolations to do the analysis. Okay, this one is just up to 15% only. Any problem? So there are some points I want to remind you. For row gradient, this is just for overflow, and the row gradients cannot be more than 15%. Okay, within this range, we can make use of this simple equation 0.3 times g to find out the correction factor. Because it is in order to keep the same vehicular speed, so that we need to enhance or increase the driving power. So that's why the correction factor here are all positive values. Okay, lots to reduce the noise effects. This is to enhance the noise effects. Okay, any problem about this one? Okay, now the road surface corrections. Okay, you know that as I told you, the rolling noise is another dominant sources to create traffic noise. For the road traffic noise, if the vehicular speed is less than 35 km per hour, the correction factor we say is -1 dBA for this bitumen or concrete type surface. If it is equal or more than 75 km per hour for bitumen surface, the correction factor is -0.75. -0.75 it means that we can reduce a very small amounts of noise effects. But if this is a concrete pavement, the correction factor it becomes 1.4 dBA. Okay, what is the meaning of TD here? TD is the texture depth, because the road pavements is not perfectly smooth. Okay, there are variations along the pavements. Similar to this one, this is the road surface texture, and normally the variation is about 1.2 millimeter. 1.2 millimeter. Okay, because there are some variations, so that's why it can induce the rolling noise effects. If it is perfectly smooth, the rolling noise effects is not a problem. And the road surface textures are the deviation from a panel surface that can affect the rolling noise effects. And we still have the no noise road surface. For any speed, we just consider that it can be reduced by 3.5 dBA. Okay. Okay. For this texture depth, 1.2 millimeter, are very small dimensions. Okay, in terms of its dimensions, how can we measure this one? If your boss asks you to measure the texture depth or the surface, how can you measure this one? Okay, they could not give you any special equipment. Can you tell me that how can we measure the texture depth on the road surface? Just use a simple approach. Okay, how to measure this one? 1.2 millimeter in real situations. Okay, we do not need to. No, we do not need to complicate the material. We just need to use this material. Sand. How to make use of this one? We put sand particles on the surface, and then we use a long volumes of sand particles and put it circular on the road surface. We have the volume, we have the area, and then volume divided by area is texture depth. Okay, very simple approach. We do not need to use any complicated or advanced equipment to do analysis. Okay, this is what we call the sand patch test, and this test has been stated in the highway department for road testing. There are 3 procedures. The first one is to use long volumes of sand particles. This is you should know the volume, otherwise you cannot do the calculations. Expect the sand particles as a circular pattern to get the area. You can measure the surface area of the sand particles, and the texture depth is V divided by A. Okay, okay, let's take a look on the real situation how to do the measurements. Okay, this is the real situations. We could use this sand patch test to measure the texture depth. And remember, this texture depth is relevant to these two equations, okay, the bitumen surface and the concrete surface. You can tell on this one, if you substitute 1.2 into these two equations, one we can get is minus 0.75 dBA. This is the reductions of noise effects. And for concrete pavement, this is positive 1.4 dBA. It means that you can enhance the noise effects, okay? Okay, now, and then we need to consider the direct distance between the receiver and the source. For the source, according to the CRT and the calculations of road traffic noise documents, they assume that the effective source is 0.5 meters above ground. But please pay attention. I could state the effective source in those tutorial questions and even in your final exam questions. So that please pay attention. But in real scenario, if you do the assessments for consultancy projects, you may consider that this is 0.5 meters above ground. And the curb here is 3.5 meters away from the walking pathway. And we do not need to consider the shelters and bus laybys. What is this one? What is the bus laybys? What does it mean? This is the bus layby, this one. Okay, if we consider this is the effective source along this dotted line, okay, the direct distance, let's say you can consider this is the effective source. If you want to do the assessment here, this is the direct distance, okay. Sometimes we need to consider the real situations. The guidelines presented here, they are just for our reference, how to do the assessments. And after we measure the direct distance here, d pi is the direct distance between R and S. We may make use of this equation to find out the correction factor. This equation is exactly equal to the chart here. It depends on this is the distance, and this is the height of the reception points. Okay, potential barrier. Even in your assignments, you need to consider the path difference to assess the effectiveness of the barrier. Okay, the path difference here is A plus B minus C. Okay, very simple. You just draw a triangle to find out the path difference. And if you can find out the path difference, we need to identify whether this is the receiver is inside the shallow zone or in the illuminated zone. Because there are still two. Because we have a chart number 9 here. There are two zones. This one is the shallow zone, and this one is the illuminated zone. Okay, let's say if the path difference delta is equal to 1 meter. Okay, when you read the data here, this is 1. The delta value is equal to 1, and the correction factor here is minus 15.5 dBA. Okay, you can read the data here directly. If the receiver is inside the shallow zone, okay, you may read the data. You can identify the path difference on the other side, on the left-hand side, not on the right-hand side. When we do the analysis or to design a noise barrier, you may refer to the guidelines on design of noise barriers. This document was issued from EPD and also the highway departments. In general, we have 4 different types: reflective type, absorptive type, and the retaining structures, or the mixed type, including reflective and absorptive type. I already explained how to find out how to draw the path difference here. If you consider this effect, normally we care about 2 issues. The first one is the diffraction effects over the tops of the barrier or on both sides of the barrier, and the other one is the transmission effects. Okay, transmissions, or those when we build a barrier here, the transmissions is one of the parameters. How to enhance the transmissions? It depends on the mass and the density of this material. And the common problems of barriers is that maybe there are any gaps along the barrier, maybe the height of the barrier along this road, they are not sufficient. They are not sufficient. The height is not sufficient. Okay, the types of the barriers, as I told you before, we have 4 different types, and when you go further about that, some people could use could design the natural barriers, such as the vegetational plantations, as a barrier, and also we can select the appropriate materials for the design of reflective barriers or the absorptive barrier. Acoustic considerations, it includes whether the height is sufficient, the length is okay, and also whether there are any gaps along the barrier, and which materials we could use to reduce the level. This is sound absorptions, and even for the sound transmissions, we still need to consider this one. Okay, in terms of the choice of barrier material, normally we have the steel structure, aluminum structure. Now, when we did our tutorial on the 1st of November, my colleague Soyi who introduced a concept to you is the use of the metal structures. Metal structures are man-made structures. Okay, we need to design a special pattern for acoustic control. This is a hot and new topic nowadays. Okay, not only in research aspect and also for practical perspective. Okay, many companies they proposed new metal materials or metal structures for the design as a noise barrier. And in terms of the transmission loss, this is another key parameter to design a barrier. We care about the fitness and also the surface densities. The largest, the highest density or the highest mass, you could increase the transmission loss. Okay, transmission loss here, it means that how much amount of sound that can be isolated by this material. Let's say here polycarbonates, the transmission loss is 30 to 33. It means that it can reduce 30 to 33 dB when sound effects passes through this material. And for the acoustic considerations, we need to consider the traffic operations. Okay, many people told that why we do not apply or install traffic sound barriers along road junctions. The major reason is for traffic safety, because if we install barriers along road junctions, it could block the driver's view. Okay, to observe the real situations along the traffic flow. Okay, so this is non-acoustic consideration, not acoustic consideration. Okay, for safety reason. And we still need to consider the maintenance, the drainage effects, and the strength and durability. The last term, it is relevant to the structural considerations, not acoustic considerations. In terms of the environmental issue, we need to consider the air quality. Why we need to consider this one? Because some of the barriers, they are in semi-enclosed view. Okay, you could block the flow of air, so we still need to consider this one. And aesthetic effects, whether this is beautiful or not. Okay, ground corrections. How to consider this one? In terms of ground cover corrections, we need to consider 3 parameters. The first one is the mean height of propagations, the bit letter H. The second one is the direct. This is the direct distance, and the last one is the proportions of the absorbing ground material I. The values of bit h, the average path height, we can calculate from this one, 0.5 times h plus 1. What is the letter h here? The small letter h. This is the small letter h, okay? Is the vertical height between the source and the receiver, okay? This one is the vertical distance between the source and the assessment points. The small letter h is the vertical distance between the source and the assessment points. So we may make use of these equations to find out the mean values of h and the values of I. Okay, it depends on how much amount of absorptive ground covers within the segments. The value is in between 0 to 1. Okay, and then you can substitute into this set of equations to select the one of them to do the calculations. This is a ground cover correction. Or make use of for this chart. This one is just for I is equal to 1 only. Okay, if I is not equal to 1, we need to make use of this equation sets. Okay, now in this one, we consider the segment here. We consider the segment here. Okay, this is a traffic road. Okay, along this is the traffic road. This is the effective source that can generate the traffic noise. And the segment here, we consider. Let's say we consider these segments. This is what we call the simple road segments. Z1 and Z2. Please pay attention. How to find out the horizontal distance between this road segment and this receiver? It should be this one, D. Okay, this is the vertical distance. Okay, why we consider this one not the shortest distance along this road segments, along this segments? Because traffic flow is a continuous flow. So the shortest distance according to the guidelines here is this one, D. Okay. Another one is the large segment areas. Okay, we still follow the same guidelines to do analysis, and they just consider that what is the small segment and what is the large segment. They just consider that if the area is more than 10 d square, the length here is 10 d, correct? And the direct distance here is d. So that if the area is more than 10 d square, we could define this as a large segment. But no matter this is a small segment or large segment, we follow the same guidelines to do the analysis. And the reflections corrections, we consider that this is 2.5 dBA. Okay, this is 2.5 dBA. When you go through the calculations of very noise effects, we still have the opposite facade. Okay, if you think that the opposite facade can contribute sufficient noise effects to the receiver, we can still consider the use of the equations presented in the calculations of vary. In this guideline, they do not consider these effects because the calculations of low traffic noise was issued before the calculations for vary noise. Okay, at that time. And the angle wheel, this refers to the horizontal angle wheel, not the vertical angle wheel. Okay, so that we use the simple calculations to find out the correction factor. And that is the end of the calculations here. Okay, what is the standard line? Okay, let me show you. In this guideline, we just simplify the approach like this. If you consider that this is a building, okay, this is a building, and this is the traffic road, we can only consider the situations like this. The direct distance, this is D, correct? If we have a situation like this, if this is road number 2, along this road, we need to consider the reception point here. How to find out the direct distance? D. Okay, I explain again. When we consider the use of this guideline, the situation must be like this to locate the direct distance here. Okay, the buildings must be in parallel with this road. But now, when you take a look on this one, road 2, the road 2 is at the same line with the reception points. Where is the direct distance? We do not know because the situations can only cater for this one. Correct? So they proposed an alternative approach is to extend this line and then create 2 imaginary reception points, A and B, and the separation distance between A and this extended line should be 10 meters. And then follow the same result, follow the same guidelines to calculate again. Let's say if we can calculate the values of the reception point 1 is 70 dBA, and at the point B we calculate is 80. We just take an average. This is the reception points. How? Okay, both of them, A and B, they are not real. They are not real. Okay, we just create 2 imaginary points that can follow the situation like this. Okay. Because when we consider the effect of road 2 to this real situation reception point R, we cannot identify what is the direct distance between road number 2 and reception point R. So that's why we need to extend the road number 2 and then create 2 different points, A and B. They propose that both of them, the separation distance should be 10 meters. Okay. You may ask, what is this one? There is an example here. If you assess segment number 1, the road segment 1 to this reception point, we can measure this is the direct distance, correct? 27.5 meters. But for segment 2, what is the effects? The road traffic noise effects generated from segment 2 to this reception point, we cannot identify the direct distance. Okay, we cannot identify. So that's why we need to create 2 imaginary points, A and B here. Okay, if we can create these 2 imaginary points, we can make the model similar to segment 1 to this R. Okay, you can see that this is the standard line, and then this is A, this is B. Once we got the values for A and B, we take an average. We can find out the values of R. We got this is the noise level to the reception points from segment 2. Okay. Okay. In the next tutorial, I will have tutorials for this one. At that time, I will explain to you more details. Okay, now we finished all the explanations of these documents, the calculations of road traffic noise. For the road mitigation noise, we may consider from the source, from propagations path and receiver. From the source, we may use V7 to use the low service noise services. For the propagations path, we may consider the use of the podium, barrier, or enclosure. For in terms of the receivers, we may make use of the innovative layouts, green roof, balconies, or double glazing window. Okay, this is for the source, no noise rope. If we use this one, we can reduce 3 to 4 dB reductions. Okay, according to the guidelines, if we consider that this is a low noise rope, the correction factor is about minus 3.5 dB. But this is normally we use it along the highway, okay, because this is specifically used for reducing rolling noise effects, and the effect is about 3 to 5 dBA. Okay, in terms of the publications path, the environmental protection departments proposed a number of approaches, such as we may make use of the multiple car parks or decking. This is what we call the decking. And the noise barrier, we have some semi-coasted barrier or fully coasted barrier. This is a common approach and the most effective approach. It can be more than 20 dBA, but sometimes for existing structures, we cannot install a new barrier along the existing roads. So although it is effective, sometimes we are difficult to achieve this one. And also, we can make use of the noise tolerance buildings, such as the use of the multi-story car parks. This is a case like this. The residential buildings, they are sitting on this shopping mall, so that the shopping mall can be regarded as a noise tolerance building, and the effect can be up to 5 to 8 dB. Okay, we still to reduce the noise effect, sometimes for public housing estate, we install this what we call the acoustic fin. This is not beautiful in terms of aesthetic design, but this is effective. Okay. And also different types of balconies, they have different performance in terms of the acoustic effects. So I just list out some of the common approach we could use it. And some buildings, public estates, they also install what we call the acoustic balcony flats. There is small plates like this one, the cantilever plates, and the use of this cantilever plates can help to reduce certain amounts of noise effects. If we cannot apply this one, we may make use of the ventilated acoustic window. The concept is so simple. We just make use of two layers of acoustic windows because they are both sliding windows, so that you can allow airflows from the outside to inside. But because you know that the propagations path for acoustic wave is a direct path, so that you can help to reduce certain amounts, like this one. Okay, we can block the direct path. And according to the real measurements, some of them can be up to 8 dB reductions. And finally is the building orientations and layouts. They proposed that we can relocate some sensitive areas such as the bedrooms and the living rooms on the other side. But please pay attention. This is not not the duties from engineers. Okay, the designs of the buildings orientations and layouts. This work should be belonging to architects. Okay. Okay, this is the end of this topic. Let's take another break and then we go back to do our tutorial tonight. Okay, let's come back to the last sessions. In tutorial number 9, you can download these two questions from the Blackboard. There are two questions. The first questions you may consider you may consider the use of these three equations and the relevant equations in the lecture notes to do calculations. Please bear in mind that there is a remark here. The noise generated from the traffic, there are two types, three different types. The first one is automobiles, the second one is medium, and the third one is the heavy vehicle. Okay, the second one and the third one, they belongs to the traffic. This is much less sensitive to the road conditions than the generated by automobiles. The main source for these two types come from the power engines. Okay. This is the first questions. For the second questions, you need to analyze the segment like this. We want to install a barrier along segment A only, and then you have to calculate calculate and compare L10 at the receiver with and without a noise barrier at segment A. Okay, what does it mean? It means that we want to build a barrier along segment A, and then you need to calculate the L10 level with and without a barrier. Okay, please pay attention. Although we consider the installations of the barrier along segment A, please pay attention. Both segment A and segment B, they could make contributions, noise effects to this receiver. Okay. Okay, please try it first, and then I will explain the answers to you later on. Okay, let's compare the answers. Okay, the first one, this is the situations. We have three different types of vehicles. One on this highways. This is a 4-lane highway. The faster lane is here and the nearest lane is here. Okay. And how to calculate the average width of the traffic lanes? We may make use of this equations as given in the questions. Okay. You can see that there are three equations here. LA for automobile, LM for medium truck, and LH is for heavy vehicles. Okay. So that the observer is located at a distance 55 meters away from the center line or the nearest link and 70 meters away from the fastest link. The highway is red and has a concrete surface with a texture depth of about 1 millimeter. And the road gradient is 3% downward. We have to calculate the total A-weighted equivalent sound level at the observer. Okay. Based on the information provided, we need to consider the road gradients, concrete surface, a correction factor, and also make use of the equations here. First, the automobile, based on the information here, we just substitute the traffic data. The traffic data for the first type is 1,200 vehicles per hour at the vehicular speed is 100 km per hour. So it is not difficult. We just put in all the relevant data into these three equations. You can find out that the level for the automobile is 59.9 dBA. The second one is 61.7 dBA, and the last one is still 59.9 dBA. Okay, any other information we still need to consider? How about road gradient? Because this is a downward road, so no any correction should be applied to all vehicle types. Okay, for upward flow, we need to consider this one because this is just downward flow. Okay, for the downward flow, we still need to use the brake to control the vehicular flow, so no any correction should be applied. Any other informations? Road gradients. These equations you can find out from your lecture logs, but this road gradient, this road surface correction factor should be applied to automobile noise only. Okay, as stated, there is a remark in the questions. For the heavy vehicles, the major noise source is from engine, not for the rolling noise, not from the rolling noise. So that's for the road surface corrections, we just make it and applied it to the automobiles only. Okay, when we apply this one, 0.8 dBA to the automobile, what does it mean? It means that the corrected LA level should be 59.9. This is 59.9 plus 0.8. It becomes 60.7 dBA. And how about the total level? How to find the total level? For the total level, we just add them together. Okay, this is the first type automobile, this is the medium truck, and this is the last one. Okay, and the total level, it becomes 65.6 dBA. Okay, any problem about this question? For what? For which corrections factor? The speed correct. It refers to these three corrections, these three equations. Okay, reference to the because when it refers to the information here, the A-weighted equivalent sound levels presented here, they are used to evaluate basic noise level, traffic flow, and vehicular flow. Okay, I summarize the equations here. Okay. Any other problems for question number 1? Okay, let's go to question number 2. For question number 2. According to the information here, we have two road segments, 7A and 7B. We want to build a barrier along 7A according to the information here, and we need to make use of these equations to find out L10 value. B and L is the basic level. This is given. CPV, we still need to consider the corrections factors here. Okay, the first question I want to ask you, if we build a barrier along 7A, do we need to cover the whole segment here? Okay, my question is, if we want to build a sound barrier along 7A, do we need to cover the whole segments? We just build a barrier from this point up to this point only, because the effective source for the whole 7A is this one, correct? The dotted line here. And the theta A, because the directions of acoustic flows is in straight line. Okay, so that if we put a barrier here from this point up to this point, you can fully cover the whole segment for this effective source. Okay, we do not need to build a barriers from this point up to this point. Okay, this is I want to share with you. Any problem? Okay, when we take a look on this one, B and L is given, this is 78.5 dBA. CPV is given, okay, 2.5 dBA. The road surface correction factor is given, -1 dBA. And CR is the reflections effect, okay, is given 2.5 dBA. CB is -10 dBA if there is a barrier. If there is no barrier, what does it mean? It becomes 0, okay? So this is also given. And CG, where is CG? Gradient, yeah. For the gradient, we do not need to, this is road gradient, okay, because this is no road gradient, so what does it mean? 0, okay? And what we just need to find out CD and CA, correct? According to the equations here, there are only two parameters we don't know. We have to find it out. Once we got it, we can find out the L10 level, correct? Okay, now how to find out CD and CA? To consider the angle of view, we first find out theta A and theta B. Theta A is so simple, okay? Theta A is so simple. This is theta A. We use a simple triangle, 30 meters over 30 meters, and then tangent. We can find out theta A is equal to 45 degrees. And how about theta B? To calculate theta B, we need to consider the whole angle, theta A plus theta B first. The whole angle is 86 degrees, so that's why theta B is equal to 41 degrees. Okay. This is step number 1. Okay, step number 2 is to find out the direct distance between the receiver and the effective source. Okay, let's go back to this diagram. When we consider 7A, okay, this is the effective source. This one is the effective source, this dotted line, okay? And then what is the shortest distance between the 7A, between the source and the receiver? This one, 30 meters, correct? How about 7B? How about 7B? Okay, for 7A, we know that the shortest distance between the effective source and the receiver is 30 meters. Because now, according to the questions, we assume that the effective source and the receiver are placed at the ground level, okay? So that's the direct distance between them should be 30 meters. How about 7B? How about this 7? Okay, it is still 30 meters. The reasons why, when I explain these segments to you, even we consider these segments, the shortest distance is D, according to the guidelines here. Okay, so no matter A or B, the shortest distance should be equal to 30 meters. So the direct distance for 7A and 7B to the receiver, both of them are 30 meters. Okay, now with the presence of the angle and also the direct distance, we are able to find out the L10. First of all, we consider that segment A without a noise barrier. Okay, before the installations of a barrier. So all of them are given. CD, you can just put in 30 into these equations. We got minus 3.47 dBA. Angle of wheel correction CA is 45 degrees, so that the correction factor is minus 6.02 dBA. And barrier corrections, now we consider that there is no barrier. So CB, it is equal to 0 dBA. And then you put all of them to the given equations, you got 73.01 dBA. Okay. This is 7A without a barrier. How about if 7A with a barrier? If a barrier, the only difference is the last term, CB, correct? All other factors, they are the same. The only difference is the last one. Okay, the last one, this one. So the difference between them without a barrier and with a barrier is one is 73.01 dBA and one is 63.01 dBA. But we haven't finished the calculations because 7B could also contribute noise effects to the receiver. Okay, now how to calculate 7B? We follow the same procedure, but for the distance corrections, it is still 30 meters. But the angle of wheel, theta B is 41 degrees. So that's why if you substitute all these corrections factors into the equation, it is 72.61 dBA. Okay, any problem? Okay, now we need to calculate the overall results. How to calculate this one? First, we calculate the total L10 level of A and B. The first case is that without a barrier. Without a barrier, at 7A it contributes 73.01 dB, and 7B it contributes 72.61 dBA. So we just make use of this equation. We got the total level is 75.82 dBA. How about the second case? For the second case, now 7A with a barrier. With a barrier, the level it becomes 63.01. So the total level it becomes 73.06 dBA. Okay, so you can compare both of the values to find out the difference. In this case, you will build a barrier. But you may have a question like this. If we do not have a barrier at 7A, why we still need to derive into two segments? If we do not build a barrier along 7A, why we still need to derive into two segments? If we do not have a barrier, actually, in calculations, we do not need to derive into two segments. We can calculate in this form. We can directly make use of these equations to find out. The only difference is the angle of wheel. What is the angle of wheel for theta A and theta B, the total angle? 86 degrees. You can check it by yourself. The angle of wheel, if we substitute the total angle 86 degrees, you can find the same results, 35.82 dBA. Okay? But please pay attention to, if we want to build a barrier, you must derive into two segments. Otherwise, you cannot get the result. Okay? For 7A without a barrier, you may consider this approach, or you can calculate directly from these equations. The only difference is that the total angle here, it becomes 86 degrees. Okay? Okay, now, what is the difference in this case if we build a barrier along 7A? The only difference is 2.76 dBA reductions. Okay, this is the total value, whether it is useful or efficient. 2.76. When you refer to this table, you can see that if there is only a change of 3 dB reductions, actually there is no any significant change. Okay, we just have a very, very minor perceptible. It means that even we build a barrier along 7A, the effectiveness of this barrier is not good. Okay, this is the full solutions, and we apply the techniques presented in the calculations of road traffic noise to solve this problem. Any problem? Okay, I will send you back these solutions to you on next Monday for your revisions. Okay, thank you.